Good morning, everybody, or probably good evening. Welcome to another video in the Let's Calc series. In this video, we're going to focus on the problem set that's devoted to concavity and points of inflection. So we're looking at the power that the second derivative holds, what it tells us about a function visually, as well as, of course, mathematically and algebraically. I guess those are all mathematically. We'll talk about points of inflection, we'll do some interesting work with numerical functions, and of course we'll address the second derivative test a little bit too. As always, I'm choosing selected exercises from the problems that I wrote. Most of these are focused on questions that are a little bit more challenging, but you may find some basic ones here too, just to go over in case you're struggling with the skill. Without further ado, let's jump into this video. Okay, the first section of the assignment is where our first question that we're going to go through in these video solutions draws from. And it's basically asking you to look at a picture and determine the concavity of each part of the function. And specifically to determine on which intervals would the function be concave up or concave down. So usually it's pretty simple if we're looking at things like parabolas, because we can literally see them. And again, I'm sure in class I talked about camels, I'm sure a little bit. We can also look at faces and look at concave up is when you're happy, concave down is when you're sad. But now herein lies the problem. When you're given a real function, you don't always just have a bunch of parabolic shapes. Instead, you've got little partial pieces, stuff like this, that we have to look at and analyze. But of course, we're going to be doing it the exact same way. So of course, what we're looking for here is we want to determine on what intervals our graph or our function is concave up, and on what intervals is our function in question, graphed at left, concave down. So in looking at this, like an easy way to start is to just kind of imagine either completing the entire thing, like you could literally complete the parabola and try to see the shape that way, or I usually just draw an arrow. I look at it as, where is this thing opening? So for instance, if I look at this left branch here to the left of the asymptote, if I draw an arrow, it's pointing downward. In other words, if we were to complete this shape and follow it, you can see that we would instead be pointing downward, and this would be concave down. So one interval on which this function is concave down, I should leave that on there. One interval on which this is concave down would be when x is less than -2. So that is one spot where it's concave down. Next we'll move into the middle. So to the left from -2 to 0, and that dot's there, you can assume that that dot's there to help us know where the points of inflection might be. So basically as I look down here, it looks like it's also opening downward. So we'd say that it's concave down for x less than -2, as well as -2 less than x less than 0. When we move to our third section here, I'm realizing I should use more color already. When we move to our third section from 0 to 2, it looks like, if we draw an arrow, it looks like it's opening upward. And in fact, you could imagine, that wasn't great, but smiling that way, we would have a smiley face. So this graph is concave up, for sure, for x values between 0 and 2. And then last but not least, we have one section left of the graph that we haven't analyzed for concavity. To determine that one, again, I look at the shape, I draw an arrow down. I mean, truthfully, I don't. I just kind of imagine the arrow there, like I did when I first learned. I see this one's pointing down as well. So I can see that we are concave down for x less than -2, -2 to 0, and also for x greater than 2. And there are our answers and the intervals on which the function has concavity. And again, for each of these things, you could have completed them if you wanted to. I think it's easiest just to look at the arrow and go from there. Now, of course, we know a lot about this. This does tell us a lot of information about the function. We know that if a function's concave up, its slope is increasing, for instance. But that's not going to be a real practical way for us to look at this, although, I mean, technically, I guess we could. Instead, it's easiest just to look at the picture and try to figure out where it fits. Or even just imagine the two different parts of the sad face or the happy face. Those kind of give you that concavity as well. So however you do it, very simple start, just kind of helping you look at what concavity itself looks like visually and graphically, so that way it kind of grounds everything else we do in something that's a little bit more graphical. Okay, next that brings us to the principal section of the assignment. This section, which I think runs from like 3 to 7 or something, with one optional exercise in there that we'll go over. In this section, you're doing all the classic work. It says for each function, find the x-coordinates of any points of inflection, determine the intervals on which the graph of each function is concave up and concave down, and we're supposed to explain our reasoning. So I'm going to explain my reasoning for every problem that we run into here for every portion. So for points of inflection, concavity upward, and concavity downward. So first of all, we have the function 3x to the 5th plus 5x to the 4th plus 17x minus 9. So we've got a 5th degree polynomial. But there's lots of different ways. Excuse me. We have a fifth degree polynomial, and there are lots of different ways a fifth degree polynomial can show up. There's, it doesn't have to necessarily go just like that. There's lots of different ways this could happen. So for the moment, I don't want to make any assumptions just yet, although I do know as a positive noodle, it's going to start low and end high. So instead what I'm going to do is I'm going to get myself to that second derivative as fast as possible, because we need the second derivative to be able to talk about points of inflection as well as to look at concavity. And we can't get to the second derivative without first computing the first derivative. So we're going to have 15x to the fourth plus 20x to the third plus 17. If your mind starts to go, but wait, I don't want to factor that, you're right. We don't have to, because we're going to find the derivative. That gets us 60x to the third plus 60x squared. So there's our second derivative. We're going to be working extensively from this. And I'm going to do a couple different things just to make it a little easier to work with. I'm going to actually factor this thing. I know there's no explicit instruction to do so, but I think it will help us out. So in fact, there is the derivative, the second derivative that we're looking at. And now here's the thing. If you set this equal to 0, you're going to get two different x values. So you're going to get x equals -1 and x equals 0. And one of the most common mistakes people make is they go, POI, and they stop. The problem here is we can't guarantee these are points of inflections until we check what the concavity is doing. There are situations, they're very rare, and we'll look at a picture of this afterwards just to make sure. But there are rare situations where a point, an x value makes a second derivative 0, but it does not actually produce a change in concavity. And that is our definition of point of inflection. A point of inflection occurs when the concavity changes signs, or specifically when f double prime changes signs. So in here, I'm going to actually create a sign chart. And again, it's not going to be a huge one. We only have two values to check. But we're going to have -1 as one spot to check. We're going to have 0 as one spot to check. I'm going to give myself just a little more room. Justification won't take much. So as far as pieces here, we're doing a sign chart, but we don't need f prime. We want f double prime here because we're looking at the concavity. We do know also that f double prime is equal to 0 at each of these places. So in a sense, these two values, -1 and 0, are potential points of inflection. They're places we might have. They're candidates for an inflection point. Now over here we have x values less than -1. We have x values between -1 and 0. And we have all positive numbers. In other words, x greater than 0. So to get our work in place, I'm going to start selecting some values for each section. I'm going to choose, I don't know, -5. This one's a little tougher, -1/2. And then I'm going to put in 42. And again, our job now is to look for the signs. We want to know, is this plus or is it minus? So to make those determinations, remember what we do is we plug into the second derivative. So if we have -5, you can imagine what we're doing is we're doing 60 times -5 squared times -5 plus 1. Remember, we don't care about the numeric value, just about its sign, SIGN. So this is positive times positive, because a negative squared is positive, times a negative. If you have two positives times a negative, you get a negative. So we know that the function f is concave down for x values less than -1. Similarly, if we plug in -1/2, you might think this is going to be bad, but remember, we're only interested in the sign. -1/2 plus 1. Okay, so as we look at those pieces, which unfortunately are a little bit too big for the section we have, so we look at that, we end up with a positive for the 60, a positive for the -1/2 squared, and in this case we're going to get a positive. So all three are positive, the product is positive as well. Finally, if we do 42, we're going to have 60 times 42 squared, which is a big number, times 42 plus 1. So positive times positive times positive gives us a positive. And at first that might not give you pause. But if it doesn't, that's actually too bad, because you're actually missing something interesting here. Even though we had two places where f double prime equals 0, there's really only one point of inflection. So answering these questions here, I'm going to actually go in reverse. I'm going to first say that our function, and actually we'll state it as formal as possible, f is concave up. In other words, the slope of f is increasing. And f is concave up for -1 less than x less than 0 and x greater than 0. And then remember, we're supposed to explain our reasoning. So our reasoning, or our reason, is because f double prime of x is positive. Likewise, we can look at the concave down section. Again, we don't have to do any fancy analysis or thinking here. F is concave down. And there's only one spot where f double prime is negative. So f is concave down for x less than -1. And our reason this time is because the second derivative is negative. Pretty standard. And so that gets us our concavity analysis, but that was fairly tame. What we were really more interested in was the points of inflection. So points of inflections occur. So in fact, let's start this. I'm going to basically write out the justification first. There's a POI at x equals, and we'll figure it out. And our reason is because. So for a point of inflection, we need f double prime of x changing signs. So there's going to be a point of inflection at some value where f double prime changes signs. And in this case, because there's only one, you could literally say changes from negative to positive or positive to negative, depending on the situation. But it's easier just to say changes signs every single time. Now looking in here, we're looking for the x value where f double prime changes signs. I see the only spot where that happens is at x equals -1. So in other words, we have one at -1, but at x equals 0, sad panda, we do not, and that's because f double prime goes from positive to positive again. So it is not an inflection point in the way that we want it to be. So now I did promise really quickly that we would look at this on Desmos and just see if this looks about right. I'd like to see if this is reasonable. Boom. So it was 3x to the 5th plus 5x to the 4th plus 17x plus 9. Okay, so kind of a weird function. You can see it's interesting. So we had 0 was the place where the concavity didn't change. So was that right? 0, yeah, it changed at -1, but not. Here, let's find some stuff here. I'm going to call this f for a second. Let's go -1 comma f of -1. And then we'll also go 0 comma f of 0. Let's see if these things look reasonable. Wow, this is a big function. This thing grows. Let's just go from -2 to 2, 0.001. And then let's talk about the y-axis. Let's go from -100. Oh, there we go. This is, oh, look at that. I did a good job this time. Okay. So looking at our stuff, these were our two. Oh, it's not in projector mode. I apologize. 2, that's fun. Okay. So there are 2 points for us to look at. In fact, I'll just label them for us. Now let's look at concavity here. On the right side, not enough. On the right side here, to the right of 0, for x greater than 0, it definitely looks like it's concave up. You can see that that looks reasonable. And to the left of -1, it definitely looks like it's concave down. In this middle section from -1 to 0, it's not really clear what's happening here. If I had to guess, I would guess that it was concave up. It just seems like that's probably true. But remember, we said it wasn't going to change at 0, so in fact it has to be concave up. Now the question is, if we zoom in enough, are we able to actually see that it is? Let's see. These are the things that happen when, let's go, -7. Oh. Trying to see if we could see the concave upness here. I mean, it's still hard. It looks pretty linear from here, but I know that it is positive. So a little bit of a bust of an explanation as an extra visual explanation, but I think that all the good stuff's there. So our approach here, what do we do? First derivative, second derivative, find the zeros or places where it's undefined, as in the second derivative. Sign chart, just felt like that was the cleanest way to check. Answers and justification. Remembering that a point of inflection is where f double prime changes signs, not just where f double prime equals 0. Put that in your head, please. Put it in. Okay. Okay, next. This now takes us to a problem that I remember writing or finding many, many years ago. And then I put it on the assignment, and then when I went to do the problem, I was like, oh, this is going to be fun. And then the weird thing happened, and it was that I had no fun. But at the end of the problem, there's something interesting there. So I do want to support you in case you want to take on this challenge. But I will say that I think the analysis part is actually easier here. It's really the differentiation that is a little bit difficult? I don't know, I thought I had something. So g of x equals x square root of x plus 3. So I want to, first of all, get to the second derivative, so we can start to talk about concavity and points of inflection. Well, to get to g prime of x, we're going to need first the product rule. You might even be able to say that they're going to need a chain rule too because of the x plus 3, but the derivative of x plus 3 is just 1, so I don't think it's going to cause as big a deal. So looking in here, let's see, product rule, we're going to have the derivative of x, which is 1, square root of x plus 3, and then we're going to have plus x times the derivative of square root of x plus 3, and that derivative is 1 over 2 root x plus 3. Again, I'm going a little faster than normal. That's because I think the focal point needs to be the analysis here, but obviously this is the product rule. From here, again, making things move really fast, if I want to differentiate this again, we got a messy factor over here. I'm just going to try to combine them all into a single factor right now. So I'm going to get a common denominator here, so I can combine as much as possible. So let's see, that's going to give me over on the left side 2 quantity x plus 3, and then plus x. Our denominator is completely the same, 2 square root of x plus 3. Distributing that in, we get 2x plus 6 plus x. That's going to be 3x plus 6 over 2 quantity x plus 3. So there's our first derivative. Don't get too excited, we're not done, because now we need to compute the second derivative. So we need to compute the derivative of this guy. So, ready for some quotient rule? Oh man, I am not digging that. But okay, here we go. I'll do it for a second time. Low d high. Look, the derivative of high is just 3 because it's linear. Minus high. D low. The derivative of low is going to be 2 over 2 square root of x plus 3. The 2's can't divide away. That's nice. All over low quotient rule. So, whew, oh boy, it's a lot there. So in fact, I think I'm actually going to prepare to bring some of these ingredients closer together just to save me some space. Sorry, pardon me. Okay, we'll deal with this in a second. Okay, so a couple different moves here that I want to take care of right off the bat is I can see that I'm going to want to find a common denominator one more time. So already I'm preparing and giving myself space to multiply up and down by the square root of x plus 3. And because that 2 divided away, that's all that's remaining in the denominator for each of those. So combining some stuff here, I'm going to get 6 from the 2 times 3. Then I'm going to have square root of x plus 3 times square root of x plus 3 is just x plus 3. Then over on the other side, we're going to have minus 3x minus 6. This is all going to be over the square root of x plus 3. And all of that is going to be over 4 quantity x plus 3. So from here, again, distributing and combining like terms, we're going to get 6x minus 3x is 3x. 18 minus 6 is 12. So far so good. Did I do that right? 18 minus 6, yeah, is 12. In our denominator, we're going to have 4, because we can combine those two denominators together. We have x plus 3 to the 1/2 times x plus 3 to the first. That's going to give you x plus 3 to the 1/2. You could likewise, or excuse me, to the 3/2. You could likewise just write it as square root times the x plus 3. That's fine too. So from there, we have our second derivative. Our job is then to figure out when is that equal to 0 or undefined. And in looking here, there's a couple different pieces. First, it's equal to 0 at x equals negative 4. You can see that because the numerator would be equal to 0 if we plug in negative 4 here. In the denominator, you can tell there's an issue at x equals negative 3. But actually, there's something even more important than that x equals negative 3 down there being a vertical asymptote. Look back up at our function. If we have the function x square root of x plus 3, that implies right off the bat that the domain of our function is going to be when x plus 3 is greater than or equal to 0, which means the only function values that we can plug in are ones that are more or equal to negative 3. And that's a really huge discovery. And the reason why is because if any x value we find here as like a potential point of inflection or an undefined spot is not greater than or equal to negative 3, we don't even need to look at it. And as x equals -4 is our only potential point of inflection, sorry, -4 is not on our domain. So it's gone. And even -3 is sort of just not there because that's the starting point for all of our work. So armed with that knowledge, we can now think about what our sign chart's going to look like. We know that everything for this function we're looking at is going to be boiled down to the second derivative. That's where we're focusing our attention. And then as far as our x values, we know the domain starts at -3, although we can't even have that in the denominator, so we'll just go -3. And then from there, there's no other place to break it apart. So this is literally just from -3 to infinity. So all we need to do is figure out what the derivative is equal to, or the second derivative, excuse me, is equal to for x values greater than -3. And then that will tell us our concavity. So looking in here, I'm going to choose x equals 0. When I do, I'm plugging it into this expression. So we're going to have 3 times 0 plus 12 over 4 quantity 0 plus 3 to the 3 halves. All of those values are positive, which means this is positive, and that means our concavity is, or our second derivative is positive. So in this case, there's a couple things we can state. This is concave up, there we go, concave up for x greater than -3. Our reason is because g double prime is positive. Other things to note, since that's the only region, this graph is supposedly never concave down. It's never frowny. It's the Leslie Knope of functions. It's never concave down, and also, since our only potential 0 spot was at -4, which wasn't in the domain, there are no points of inflection. So for all that work, we're supposedly finding a function that is simply always concave up. And if that seems unlikely to you, let's graph it and take a look. Let's do this in a more standard zone here. We put in, I think it was g. If we let g of x equal x square root of x plus 3, look at that. We definitely have a concave up function here, a graph that always has its increasing slope and is always opening upward. And of course it starts at -3, there is nothing to the left at all. So with that said, interesting problem for sure. It's a good opportunity to kind of put some differentiation skills to the test, even some algebra skills to work through there. And then it was kind of wonky because there were only certain x values that were allowed, even though certain ones were showing up as potential important points. So again, this was optional, but if you're looking at it and digging into it, good for you. I think you should. It's a good question. It's just a little more time consuming than I'd like from your assignment. Okay, that brings us to question number 7, which is a piecewise function. And I have basically committed to having a piecewise function on every single assignment that we do this year, or at least I'm trying to. But the work here isn't going to be actually as bad as you might expect. So in our situation, we've got a function p of x that is x cubed when x is less than or equal to 2, and is some positive parabola when x is greater than 2. So not the hardest combination of functions to go through, but still something that we should look at and compare a little bit. So in order for us to work, the first place we need to get, of course, is to compute the second derivative. So we're not going to have to worry about differentiability or anything here either, by the way. We just need to look and see what's happening. So let's see, if we want first p prime of x, that's going to be equal to 3x squared when x is less than or equal to 2. And it's going to be 4x minus 10 when x is greater than 2. Likewise, p double prime of x is going to be equal to 6x when x is less than or equal to 2, and 4 when x is greater than 2. So a couple interesting things here. Remember, in order to check for potential points of inflection or even just set up our inner sign chart to analyze the second derivative, we need to figure out where that second derivative is equal to 0 or is undefined. And it's easy to notice both options. For p double prime of x, 6x equals 0 at x equals 0, and x equals 0 is less than or equal to 2, so we definitely have one place, x equals 0. The second one would be, since we have a continuous derivative for above 2 and below 2, second option would be 2. Well, if we compare the limit as x approaches 2 from the left side of p double prime of x, we get 6 times 2 is 12. Whereas if we do the limit as x approaches 2 from the right side of p double prime of x, we just get 4. And since 12 doesn't equal 4, that implies that p double prime of 2 does not exist. Sorry, I'm running out of space. So p double prime of 2 does not exist, so the other place we need to consider is at x equals 2. So there's two places for us to split up our second derivative and do our analysis. So doing a quick little sign chart here. Again, I really like sign charts for these, and I'd be much more comfortable with a sign chart than trying to just reason out what this function looks like itself. So we're comparing values of p double prime of x. As far as the x values, we have 0 and we have 2. We noted that at 2 the function's second derivative was undefined, whereas at 0 the derivative was 0. Now we need to start to look at what happens when x is less than 0, when x is between 0 and 2, and when x is greater than 2, which isn't trivial. There's a little bit of work to do there. So as far as pieces for us to work through, it's important to remember which part of the function we're looking at. So in here, we said that x cubed was true for x less than or equal to 2, and specifically that 6x is the second derivative when x is less than or equal to 2. So for right here, we're going to be using p double prime equals 2x, excuse me, not 2x, 6x. So if we plug in a number that's less than 0 into 6x, like -1, we're going to get -6, which is negative. If we plug in a number between 0 and 2, like 1, we'd get 6 times 1 is positive. So on the other hand, last part of this one's going to be kind of funny, in fact. This last section, for x greater than 2, is just when p double prime is literally equal to 4. It's just the constant 4. Well, 4 is always positive, so for sure, no matter what number we pick in here, it's going to be positive as well. And with this in place, we've got all the information that we possibly need. So a couple different things here. I'm going to actually avoid the justification just for the sake of time. I'm not feeling real great, so I'd rather cut that short a little bit. So things that we can draw out of here, there's a point of inflection at x equals 0. And we can see that because p double prime changes from negative to positive. I guess I could write that in there. It's less than I'd like to say, but oh well. Next, of course, we've got the concavity. This function is concave up when x is between 0 and 2, or x is greater than 2. And of course, our reason is that p double prime is positive. I guess I'm doing it all. This is concave down when x is less than 0, and that's of course because p double prime is negative. Now with this particular function, I encourage you to take a chance at actually sketching it out. I did do that earlier when I wrote the question though, and I can tell you right now, since we've got the parent graph here, I believe this is what the function looks like. So concave down, concave up, concave up. So I know that it's there. Again, you can put it in Desmos on your graphing calculator. Have fun with that. Okay, next, move on to question number 9. Question number 9 is a direct opportunity, or is an exact opportunity to use the second derivative test or to practice using the second derivative test. So in 9, you are instructed to find the critical numbers of f. So we are talking about the critical numbers of f of x. Oh, excuse me. Then we're supposed to use the second derivative test to classify each one as either a relative max, a relative min, or neither. So this is the other technique that we have to determine if some value is corresponds to a relative maximum or a relative minimum. Yesterday we looked at the sign change in f prime and used it to conclude there. Today we're looking at the second derivative test. So of course, if you want to use the second derivative test, the first thing you need to do is find the second derivative. So first derivative is an essential spot. Oops, sorry. Started to write the function. There you go, plus 4x minus 4. So remember, we need to figure out the critical numbers to get anywhere here. So we need to factor this. It's going to be 3x squared, let's see, split the middle, plus 6x minus 2x. I think this will do it. That's going to factor into 3x minus 2 and x plus 2. Let's see, 3x squared plus 6x minus 2x is plus 4x minus 4. Yes. Okay, so there it is. Its first derivative is nicely factored. And if that equals 0, we get that x equals 2/3 and x equals -2. So we have two critical numbers. So that was our first step. In fact, I should write that in here. If you didn't like that I didn't write critical numbers first, and you say something about it, that makes you a critical number. So now that we have our critical numbers, we're supposed to use the second derivative test on them. So to use the second derivative test, we of course need the second derivative. And that's easy to calculate. It's literally 6x plus 4. Right? We're just taking the derivative of 3x squared, 2 times 3x to the first, and derivative of 4x is 4. So with that in place, we can now look at each of the two pieces. So first we'll look at x equals 2/3. So we know that f prime of 2/3 is 0 because that's what it means to be a critical number. Like that's literally the definition. Our interest first is what is f double prime of 2/3? Because we're going to use the concavity at that critical number to check whether or not the function is concave up or concave down. Because at a critical number, that corresponds to either a maximum or a minimum. So in our case, if we want f double prime of 2/3, that's going to be 6 times 2/3 plus 4. That's 12/3 plus 4, which is 8. And 8 is positive. So from here, what we've just shown is we've shown, here, we'll write this as like an explanation. Because f prime of 2/3 equals 0, so again, as I state my answer here for the first one, it's important that we do say because f prime of whatever equals 0, because otherwise we can't apply the second derivative test. It has to be at a critical number. So because f prime of 2/3 is 0, and f double prime of 2/3 is greater than 0, f has a, we'll say, local, now we got to figure it out. So we have a critical number. In this case, the second derivative is positive, which means that we are concave up. And if something is concave up, opening upwards, means that you've got a low point. So this is actually going to correspond to a local minimum at x equals 2/3. And as far as the explanation, that's our explanation. We cited that 2/3 had a 0 on the first derivative and whether it was positive or negative on the second. So there is our answer for the first one. Or I guess technically this is the piece that's most answering. So there it is. Okay, following a similar pattern, I'm going to have to conserve space a little bit better so I don't run out of room or right over my face. So over here, if we want to check x equals -2, f double prime of -2 is going to be 6 times -2 plus 4. That's going to be equal to -8, and -8 is less than 0. So from there, what that means is we can then justify, since because f prime of -2 is equal to 0, so we had a critical number, and f double prime of -2 is less than 0, f has a local max, as opposed to an uncle max, at x equals -2. Voila, there's our work. You can see that what was important here was first that we remembered that to get the critical number, we did have to use the first derivative. So we were finding the first derivative zeros, or undefinedness, potentially. Second, we were finding the second derivative. And then third, we were plugging those critical numbers into the second derivative to check the concavity at that point, knowing that at a critical number, if the graph is concave down at that critical number, we have a local maximum, because it would be at the high point, whereas if we are concave up at one of those critical numbers, we have a local minimum. And there is 9a, and again, 9b will be the same structure as what you just saw here. Okay, that brings us to question number 10. 10 asks us to write the equation of the tangent line to this function. So, hey, it sounds like a totally easy review question here. Equation of the tangent line, x cubed minus 2x squared plus 6x minus 4 at its point of inflection. Oh, there's the challenge. We have to figure out its point of inflection, then we got to write the tangent line there. So this is going to be an interesting one. In fact, I've been watching some good video game design videos on YouTube, and I've been reading a lot about reasons why one of my favorite games of all time, Donkey Kong Country 64, is bad. And they say it's bad because there's so much backtracking. Well, this is a backtracking kind of problem. Got to be honest with you. So we want to find the tangent line here. In order to do that, we're going to need to find, of course, the slope at some point. So let's just start there. The slope equation y prime is going to be 3x squared minus 4x plus 6. We don't need to factor it or do anything else with it for the moment, because again, we need to know more about this point of inflection spot. Second, we need to use the second derivative and compute it so that we can actually figure out where the point of inflection is. So in here, that's going to lead us to a second derivative of 6x minus 4. And if we set that equal to 0, taking advantage of the fact that this polynomial is going to always have one point of inflection, there won't be any distractor ones, we're going to get that x is equal to 4/6. In other words, x equals 2/3 is the only point of inflection. And again, if you're someone that doesn't trust this, you're welcome to make a quick little sign chart and check to make sure that it does work. I think in my written solutions I may have done that. Let's just do it here because I'm sitting here and I don't want anyone to judge me for not doing it. So let's do 0 and 10. If we plug in 0 to our second derivative, we get -4. If we plug in 10, we get 60 minus 4, which is positive. So we do have a point of inflection since f double or y double prime changes signs at 2/3. So now that we have x equals 2/3, you can imagine that what we're ready and trying to do here is we're trying to construct our tangent line. We've got to do y minus something equals something, x minus something. Well, now that we know that the x coordinate of the point of inflection is 2/3, we can fill that portion in. Next thing we're going to do is we want to figure out what is the actual y value at this point of inflection. So I'm going to compute y of 2/3. Granted, I didn't make this easy on you because of all the computation and arithmetic you have to do, but it's good to do that sometimes. Just not asking you to do it a lot. I understand. Yeah. Okay, so here's our stuff. So this is going to be 8/27 minus 4 times 2 minus 8/9 plus 12/3 minus 4. Oh, hey, look at this. 12/3 is just 4, so 4 minus 4 is 0. So we really only have to deal with that portion. So to deal with it, I'm going to multiply up and down by 3 on the second fraction, and that's going to give me 8/27 minus 24/27, which is equal to -16/27. And that is our y1, so we can go ahead and make this y minus a -16/27. So good job, we got our y value. What we don't have, though, is we don't have the slope yet, and that's a pretty essential ingredient to any tangent line. A friendly neighborhood tangent line needs friendly neighborhood slope. I don't know what that's a reference to, except for Spider-Man, so who knows. So if we want y prime of 2/3, we want to know what the slope is at that point, so we can construct a full tangent line. Our derivative was 3x squared minus 4x plus 6. So 3x squared minus 4x plus 6. So in looking in here, trying to simplify things, we're going to get 3 times 4/9. We're going to get minus 8/3 plus 6. A couple things I see that are kind of nice. 3/9 becomes 1/3. So 4/3 minus 8/3 plus 6. We'll do that over thirds too. That's going to give us, it looks like 4/3 minus 8/3 plus 18/3. So combining all of these pieces together, did that right? Yeah, I guess I did. It's going to be 10/3 plus 4/3 is 14/3. So after all of that work, we have our tangent line. And you know what, just to be safe, let's see if that actually worked. Like, we haven't been doing visual on every problem, but we can here. So our function itself was 3x squared minus, no, that was the derivative. Excuse me, x cubed minus, was it 2x squared? 2x squared plus 6x minus 4. Let's make sure it was plus. It was plus. Okay, so if there's our function, we wanted to see that the tangent line was y plus 16/27 equals 14/3 x minus 2/3. So the question is, does this actually seem to be, does it look tangent? Sometimes it's hard to tell when you're zoomed in like that, but it looks pretty darn tangent to me. So I feel pretty good about what we've done. I think we found the right answer, and I think we've got this complete. The important thing was just to do every single step all the way through the second derivative, and then work backwards, kind of go back, plug in, and find the y value and the slope value at this particular point. Alrighty. Okay. Next, moving on to question number 11. I'm going to do, I think, parts A and C, because B is almost identical to A, just in a different direction. So in 11, you're provided a table of values, another one of those consistent things we try to provide you. It gives values of the twice differentiable function f of x and both its first and second derivatives. So there's a couple different values in there. fact, I see a bunch of stuff. I even see a k in there. I'm not sure if that part of the question still remains, but it was in there originally. So in 11a, you're asked, does f have a relative maximum, relative minimum, or neither at x equals 3? Explain your reasoning. So in this case, given, well, let's just see what we have. So what do we know about f of x at x equals 3, besides the fact that it's twice differentiable? Well, f of 3 is equal to -5. So does that tell us much? No, not really. It just tells us what the y value is. It tells us it's defined. That's helpful. But it doesn't really provide a whole lot otherwise. So next question is, what about f prime of 3? What does that equal to? What says f prime of 3 is 0? What that tells us is that x equals 3 is a critical number for f of x. So anyone that's learned to count would know that 3 is critical to learning numbers, but this is specifically a critical number for our function f of x. So that means this is a place where we could have a relative maximum or relative minimum. This is a candidate for a relative extremum. So that's helpful. So now our problem is, if we were to try to analyze this from here and try to look using the first derivative test, we wouldn't be able to. Yes, we know what's happening on f prime at -1 and what's happening at -3, but we don't know what's happening in the middle of those two numbers, or these two numbers. There's just a lot of space in there where the sign could change multiple times. We just don't know. So the only thing that we can use otherwise is the last bit of information we have about f of x at 3, and that is the second derivative of f at 3. And our second derivative in this case is -e, which for our purposes, if you don't know the value of e is 2.7182818284590235. Oh, okay, I lost track of it, but something like that. So our second derivative is -2.7-ish, but most importantly, that means our second derivative is negative. So if our second derivative is negative, that implies that our graph, or our function, is concave down at that point. And if our function is concave down there, we have a shape that looks like this, and our critical number is right there at the very top. This is a relative maximum. So, and it takes a little getting used to. Negative concavity corresponds to a maximum. It's kind of counterintuitive, but it should make sense. Concave down means that there's a place at the top. There's a high point up there. So in reality, what we've just shown is that there is a relative maximum at x equals 3. So in other words, for our explanation, f has a relative maximum. I'm going to just call this a rel maximum at x equals 3. And we know the reason is the second derivative test, but just to make sure that we clarify this properly, it's because first we established that we are at a critical number at 3, so because f prime of 3 equals 0, and then second, f double prime of 3 is less than 0. And if you were looking for like a one-stop shopping like name for that reason, if you want to put in a name there also, you could say this is because of the second derivative test. It's not my preference that you say second derivative test. I want to see the specific information here noted, even though it's given in the table. But this is a good explanation for what's there, and the important part is we determine that there's a relative maximum there. And we use the second derivative test. And I'd say that your biggest clue that second derivative test might be something valuable here is if you're asked this question and you're given information about the second derivative, that's a time when the second derivative test is a good call. Basically, if that second derivative is accessible and easy to get, then that's a good candidate for using the second derivative test. But in any event, 11a, not that difficult, just a matter of lining things up and then reading the info out of the table and knowing what each value actually represents and tells us about the function. Okay, next that brings us to question 11c. This is another favorite of mine. We are asked to explain why the graph of f of x has a point of inflection for 3 less than x less than 5. So in sitting here, we want to focus our attention right here. So we're looking in that area, and it's worth reminding ourselves that f has a POI if f double prime of c, if f double prime changes signs. So I'm bringing that up as kind of a starting spot because that'll kind of help us reason our way through here. So what do I know? Like looking at the information here. Well, f double prime changing signs would also mean that f double prime would have to equal 0 at some point in the middle too, right? I mean, in order to change signs from negative to positive or positive to negative, you'd have to go through 0. So my thought is that's what we need to show. we need to show that there's a reason, or that there must be a place where f double prime of x equals 0 on 3 to 5. And when I think of that, does that not sound a little bit like the intermediate value theorem? Trying to show something equals 0, and we've got information about the other two. So that's going to be my thought process here. I want to use the intermediate value theorem to try to make this conclusion. So reminders, what are the things that we need? Intermediate value theorem requires, of course, first continuity. So we'll have to be careful about what we're talking about there. And second, it requires a boundedness. It needs to be between the appropriate y values that we have, or at least the desired one needs to be in there. So looking at our pieces here, what do we know? So can we get both of those pieces to use it? Well, we're interested in the second derivative's value. So in here, can we conclude that f double prime is continuous? Well, as far as our reasons why, we are told that the function is twice differentiable. So if f is twice differentiable, I really want to shorten this, so I'm just going to go twice diff. That implies that f double prime is continuous. Because being able to use and compute the second derivative for all values is the same thing as saying the second derivative is continuous itself. So in other words, we have continuity for f double prime, because our ultimate goal is to show that f double prime equals 0. For boundedness then, we need to look at the surrounding area. So f double prime of 3 is equal to negative e, we used that earlier, and f double prime of 5, better be positive, yes, is equal to 7, so that's positive. So 0 is in between, so we are in fact bounded as well. And that's all we needed. That was the requirements for the intermediate value theorem. All that's left for us is to say it in the correct and a formal way. So in here in our explanations, actually let's start in a different place. F is twice differentiable, and I'm going to use the abbreviation diffable to save timeable. So f is twice differentiable, so f double prime of x is continuous. And we just showed f double prime of 3 is less than 0 is less than f double prime of 5. So those are the two requirements. We're stating this properly by guaranteeing and explaining why we have continuity and boundedness. Thus, by the intermediate value theorem, and I'm going to write it one time since I didn't earlier, but again, you can use the IVT, I believe. By the intermediate value theorem, not to be confused with the mean value theorem or the extreme value theorem. By the intermediate value theorem, f double prime of c equals 0 for some c in 3 to 5. And now we have to be a little bit careful here. That's not quite full enough, because what we really need is the f double prime to change signs. And thus, f double prime changes signs at c. So by definition, sorry, this is so low on the computer or on the screen. So by definition, f has a POI, or a point of inflection, I can't spell. Suddenly lost the ability to spell. Of inflection at x equals c in 3 to 5. So again, I probably wrote a little bit more than I needed to, but I think the thinking here is what's most important. And being savvy using the intermediate value theorem as well. Being comfortable invoking it in an appropriate spot and verifying it based on the small bit of information we're provided about a function. But there is 11c, the newest appearance of the intermediate value theorem. Okay, next we have question 12. And question 12 took me a long time to write properly, not 12a. 12a is a classic question. 12b I had a hard time asking, so I'm less worried about that. But for 12a, we're in a question that's shown up many, many times in many, many interesting places. So consider the twice differentiable function h. So since h is twice differentiable, we know the second derivative exists, so it's valid to ask about concavity. In 12a, we are asked, based on the table at right, is the graph of h concave up or concave down? Explain your reasoning. That's interesting. So now as a heads up, like I've asked this question for many years in many different ways, and again, I've mentioned Mighty Chen before, as well as Lawrence Lee, a couple people from that class of 2016 did a really nice job. And something that I believe both Mighty and Lawrence did, if memory serves, was they weren't exactly sure how to approach it right off the bat. So what they did was they figured, okay, well, let's just graph it and see what happens. So they went, if that's 20, 0, 20, then 110 would be halfway down. Then 2, 5 would be halfway from there. Actually, that's probably about right. Then 3, 2 would be a little under halfway there. And 4, 1 would be a little under there. And they just went, well, what does it look like? Does it look reasonable? In this case, if you connect those dots, it looks to me like F, or in this case H, is concave up. And I realize now, looking at this table, this should say H. So we'll fix that on the assignment. So H. In fact, let me make a little note here on the thing so that I fix that. Need to fix H of X. Big circle. Okay. So for H of X, so it looks like it's concave up. And in fact, it is concave up. That is an absolutely valid way to approach the problem. The only problem with that is it's not as easy to see. And if I'd given you numbers that were a little bit closer, or you didn't have access to it, or you just were struggling to graph them accurately, you might get a bad picture. It might look linear or potentially even concave down. So instead, the method I'm going to use relies on some heavy work with the mean value theorem, but really it's focused on doing something really, really simple. It's approximating the first derivative and seeing what's actually happening there. So let me show you what I mean. So we have a table with values of h of x. I'm interested in getting a table of values involving h prime of x. In fact, I'm going to even change the color here. So I'm interested in a table with h prime of x values. Now, we don't know enough about the function to actually find exact values like instantaneous rates of change. So all we can do is approximate the instantaneous rate of change using the average rate of change, something we've done before. So what I'm going to do is I'm going to calculate the average rate of change on each interval. So for instance, on this first interval, we'll have 10 minus 20 over 1 minus 0 is equal to negative 10. So in other words, h prime of x is equal to negative 10 for some x value on the interval from 0 to 1. So by the mean value theorem, if you care. So that's our first one. Next, we'll go 5 minus 10 over 2 minus 1 is equal to negative 5. So again, by that mean value theorem, h prime of x equals negative 5 for some x value between 1 and 2. Let's do it again. Again, I'm running out of space here. I needed to stretch that a little more. Oh well. We're going to have 2 minus 5 over 3 minus 2 is equal to negative 3. And last but not least, we've got 1 minus 2 over 4 minus 3, which is negative 1. So these are our values of h prime. And at this point, something you can see is if your slope, h prime, is going from negative 10 to negative 5 to negative 3 to negative 1, you can conclude right there that h prime of x is increasing. And this was one of our explanations and rationales. So if h prime of x is increasing, that means that h is concave up. So we've now been able to explain why this is concave up using one of the properties that defines concavity. There's actually one more. So really, you've seen two approaches here to take. I'm going to show you a third one too that I didn't even do in the written solution. So you know this process we did just to generate this, calculating out average rates of change to approximate the derivative? Well, we can actually do exactly the same thing with the derivative of h prime of x. In other words, we can approximate values of h double prime and see whether they're positive or negative. So this one can be a little tricky because our numbers are all negative, but let's play along for a second. Again, we're still changing x by 1 every single time. So this is going to be negative 5 minus a negative 10 over 1 minus 0 is equal to 5. Next one, we have negative 3 minus a negative 5 over 2 minus 1. I think I'm doing that right, yes, is 2. Going down one more, negative 1 minus a negative 3 over 4 minus 3 is equal to make sure I do this correctly. I feel like I'm missing something here. So that was from, well, it doesn't really matter. We can get our value here. This is going to be 2 as well. So what do you notice about h double prime? And again, using mean value theorem things to guarantee it. Hopefully what you're seeing is that h double prime of x is positive. Every single time we get positive second derivative. Even if it's an approximation, that still has to represent the second derivative at some value because of the mean value theorem. That also confirms to us that h is concave up. So in this particular situation, you've got 3 approaches you could take. And for this problem set, there's no reason you couldn't use any one of these 3. I would accept all of them when we're here. Just know that in the future, the better explanations are the ones that are right here, simply because you can put them into words and use explanations and definitions to explain them. So at the same time, though, all 3 of these things were accurate and good ways to approach this problem, which could otherwise be kind of challenging. Okay, last but not least. So, and again, this is a question that I'm not worried about. Like, it comes up a little bit more naturally later on. Having trouble forming the question, so I'm just going to describe it really quickly and kind of give you the overview. So it says, let t of x be the tangent line to f, and that was supposed to be h. So I got to fix that too. H. There. To h of x at x equals 2. Use a diagram to decide whether t of x is less than or equal to f of x, or t of x is greater than or equal to f of x. Well, and again, changing those things to h's. Gee, I should just change the first one to f, shouldn't I? Oh well. So what do we just discover? H of x is concave up. We found that out in part A. The question we're asking here is, will the tangent line be larger or smaller than the graph of h, given this information? So now we don't know a whole lot, although we did have that nice little sketch of the function from before. So there is a concave up function. It's more or less what our function looked like, sort of exponential, but kind of reversed, maybe even part of a rational of some kind. So there is our function. If we draw the tangent line at any point, but even specifically at x equals 2, you can see that the tangent line is less than or equal to the function itself. Right? I mean, you can see that pretty nicely. It's clearly below, and our function was concave up, so there it is. But now here's the interesting thing. If our function hadn't been concave up and decreasing, but concave up and increasing, let's see, I gotta do that right. But concave up and increasing, we'd actually have the same phenomena occur. If we drew the tangent line right here, you can see that once again, the tangent line is less than or equal to the function. So it doesn't matter whether your curve is increasing or decreasing. All that matters is that the concavity is consistent, and that will guarantee the tangent line will be below if the function's concave up. And even though you weren't asked this question, because I couldn't figure out a way to ask, you could actually do the same thing and look at what happens if the function is concave up, or concave down. So if concave down, get down on him. If h of x concave up, FYI it's not, but if it was, look at these pictures. So if we want to do concave up but increasing, or concave up but decreasing, or sorry, we're supposed to be concave down but decreasing, then draw a tangent line. Draw a tangent line. Bad tangent line. There we go. Notice in both of these cases, the tangent line itself is greater than or equal to the curve, no matter whether it's increasing or decreasing. So just something interesting to note. It's just kind of a fact to get in there. Again, I don't think the question was asked in a particularly great way. I'm not proud of that question. It's probably one that I'll come back to sooner than any other one on this assignment, but at least I wanted to expose it to you once. We've talked about it a little bit. It's something very visual that you can get by drawing things out and exploring, but again, not super concerned about this question. What I am concerned about is that hopefully you found good, valuable information in this video. Without further ado, I'm going to call it a night. Hope you've enjoyed what you've gotten, and have a great night.